No? Great.
Mhm.
Okay. Hello, everyone. I hope you're enjoying this virtual conference. I'm Wendy Liu, Professor of Biostatistics at the University of Toronto, Canada. It is my great pleasure to chair this session, sponsored by the Statistical Society of Canada, SSC. Before I start, I would like to give a very brief introduction about the speaker, Professor Tiffany Timbers. Tiffany is a faculty member in the Department of Statistics at the University of British Columbia, I'll briefly as UBC, in Vancouver, Canada. In addition to teaching, she co-directs the master's program of data science at UBC. Prior to joining UBC as a faculty, she completed her postdoctoral training at UBC and Simon Fraser University after obtaining her PhD in neuroscience, also at UBC. She's a true Vancouver person. Tiffany is an internationally recognized leader in teaching data science. She was recently awarded with the SSC's Early Career Educator Award just this year. If you're teaching courses on data science, I highly recommend you check out her website. She co-authored 2 textbooks. One is titled Introduction to Data Science, and the other is titled Python Packages. Both are available at her website and also available as published texts through CRC Press. In the interest of time, for more details about Tiffany's research interests, publications, and her leadership roles, I will refer you to her website, which I will send the URLs through the chat shortly. So today she's going to tell you about 10 simple rules for teaching data science. All right, so over to you, Tiffany.
Thank you. Thank you for the introduction, Wendy, and thank you to the organizers for this great meeting. I'm very honored to be part of it. I'm going to share my screen now and let me know if everything looks okay on your end.
Yep, looks great.
Excellent. Okay. So as Wendy said, the talk title I have for you today is 10 Simple Rules for Teaching Data Science. And so these 10 rules that I'm going to present to you are not rules that I have necessarily I'm not the first person to do this thing, but I'm trying to collate 10, I think, really good tips, I guess, for teaching that I've seen other people do and then used in the classroom too with some success. So the first rule that I'm going to talk to you about is teaching data science by doing data analysis. So what do I mean by this? So I mean in your first lesson, not in your third lesson, not in your 10th lesson, not at the end of the semester, but in your first data science lesson, get the students to load some data, do some mild data wrangling, and make a plot. Why do I suggest this? Because it's extremely motivating to students. In the beginnings, students have signed up to do data analysis or to do data science because they're interested in asking and answering questions about the world using data, and they don't necessarily have enough knowledge to care deeply about small things like type and whether you're using tidyverse versus base R, whether you're using R versus Python. So show them something interesting early on, hook them, and then they're going to be begging you to answer those questions for them. So an example of this is shown in the slide here. So in our first lecture in Introduction to Data Science, DSci 100 at UBC, and this also comes from the first chapter of the companion textbook for that, Data Science, a First Introduction, we get the students to load data from a CSV, do some light data wrangling through filtering, arranging, and slicing, and then create a plot to answer a question about Indigenous languages in Canada, how many of them are there, how many people are speaking them as their mother tongue. So this is not a new idea for me, as I said. I was first inspired to do this through following what David Robinson was doing in some of his online courses. He talked about how it is just so much more intuitive to use the tidyverse. His case was using the tidyverse to get students doing things really quickly in a readable way, as opposed to base R. That's not the argument I'm necessarily making today, but his reason for this is you can get people doing interesting things really quickly. Jenny Bryan, another pretty well-known or extremely well-known data science and R educator, turned software developer, has also tweeted about not front-loading the boring foundational stuff in courses. So do realistic and non-boring tasks and work your way down to the more boring stuff. Students are going to care about that more boring stuff once they get a bit of experience. So on each of these slides, you'll kind of see a pattern that I'm going to have some, if you're really particularly interested in a given rule, you can follow these links. And I'll share a link to my slides at the end of this talk, so it'll be easy for you to find these. So my second rule is to use participatory live coding. So what do I mean by that? So I think that when you are doing something with code in the classroom, instead of popping it up on the screen and just running it, or even showing it in a static slide, actually open up an editor, type it out, and narrate the code as you are teaching it. Have the participants follow along as well. The reason for this is it demonstrates the processes. You can talk about why you're doing things in different ways as you're doing it, to layer that on top of the code itself. And you're likely going to make mistakes as you live code, and that's actually a good thing. It helps you appear human to the students because they're going to make mistakes too, and so they will better identify with you. And then they'll also learn how you solve the problems when you make mistakes, which they'll be able to leverage and use later in their careers. This simple rule comes to us from the carpentries. So I saw this first as a software carpentry workshop participant and later as an instructor. And it's used in all of their workshops across the world. The third simple rule that I bring you is giving tons and tons of practice. So what do I mean by that? Give the learners many, many, many problems to solve, probably many, many more than you think that they might need. The reason for this is that repetition leads to learning. That's not just in humans, like my background is in neuroscience, in looking at animal behavior, and across the animal kingdom, repetition leads to learning. So students really need to do things many, many times to understand and then to perform those tasks. So here's an example from my intro R course. I teach this at both the undergrad and grad level. And when I'm teaching students to read in data, I get them to do this in one exercise, six different variants of a very similar file. So the students have to investigate each file, look at the spacing, look if there's metadata, look at what type of file it is, and really figure out how to do this. And so they'll do this in a worksheet, and then later they'll also do it on a different set of files in a lab assignment, and then they'll have to do this on their quiz as well. So many, many practices. Inspiration from this comes from the Swirl R package, which was the first time I saw something like this. So this is a really cool R package made by Sean Cross and others, where you install it in an R console and run it through the R console, and under different topics in the R programming language, it'll prompt you with many questions, and then you answer the questions in there, and it will give you hints, and it will tell you if you're doing things correctly or incorrectly, which is also kind of neat and leading into what I'm going to talk about next. If you're interested in seeing examples of this beyond Swirl, again, I have more examples here. So we have some worksheets from our Intro Data Science course, and then there's a great online course by Julia Silje for machine learning case studies, and then Greg Wilson has a great book called Teaching Tech Together, and he's got a whole section on different types of coding exercises, so you can find different ways to present the same content to your students, and they get to practice different aspects of it. Pairing with giving lots of practice, you also want to pair that with tons and tons of timely feedback. And practice without feedback has limited value. So how can we give tons and tons of timely feedback? One way we can do this is through automated software tests. So in data science, a lot of the problems we're going to give students to do are working through code. And so we can write software tests that if a student gives a particular answer and it's wrong in this particular way, then we can give this feedback back to the student, and then they can maybe try again and solve the problem in a different way. Here's an example that we use in one of our courses where the students were given some ggplot code and it was jumbled up in the wrong order, and they have to rearrange it. And in this rearranging it, the student is missing, somehow missing the plus sign to add another layer, and that ends up with a poorly formatted access type title. When they run our test, then they get some feedback that there's a problem with one of the access labels. So that will direct the student's attention back to look at hopefully at the label code. They can fix it, and then they'll get a message that they were successful in fixing the code, and it's what we've expected. The first time that I had heard about doing something like this was there's a wonderful in addition to like different types of coding exercises in Greg's Teaching Tech Together book. There's also a section, or there's many sections where he's done a very thorough review of the literature. And in that review of the literature was this idea to do these automated testing. And there seems to be quite a convergence of this in the computer science field and coming into the data science field. So we actually have lots of tools, open source tools now to do this. So Learn R is a package you can do this with in the R programming language. And then there's NBGrader and OtterGrader, which are language agnostic tools, or at least work with R and Python for providing these kinds of feedback to students on their practice problems. Rule number 5 is to use tractable or toy data examples. And so what do I mean by this? So when you're introducing a new tool, a new method, a new algorithm to students, you give them data to learn this that has a countable number of things that will kind of fit inside of our working memory, so students can track where everything is going through different steps of the algorithm. And this allows students to see how the elements are manipulated and really get the intuition for these things. An example from one of our courses, the Introduction to Data Science course, where we teach k-means clustering, we use the Palmer Penguins data set to introduce that. But instead of throwing that entire data set that has hundreds of observations at students, what we do initially is we subset that to just a handful of observations, like shown here on the screen. And then, we can walk the students through what happens to these observations at each step of the algorithm. And students can, very clearly see from step 1 to step 2 to step 3 to step 4, what is happening with those observations, and build an understanding and an intuition. Inspiration from this comes from Jenny Bryan's great dplyr join cheat sheet that she created in the Stat 545 course at UBC. And so in this example, she's teaching all the different joins from the dplyr package. There's left joins and right joins and fold joins and inner joins and semi joins, and depending on the direction, you might end up getting a different result. And so to help students understand these things, it's really hard to get an idea of what's going on in all these things that are also similarly named when you have really big data sets. So she created an example cheat sheet where there's only like 6 rows in one data set, 3 rows in another data set, and then she goes through all the different possible joins and shows the output of it. And so as a learner looking at this becomes very tractable and easy to understand. Now, after you've used a toy or tractable data set and the students have found conceptual understanding of the new method or algorithm you're teaching them, the next thing I think to do is to use a real and rich data set paired with like a real question. But as you're doing this, make sure that that data set is also accessible. So what do I mean by that? Is that you want to have a data set where the question is something that a real data scientist, either in academia, industry, government, would really want to answer. It's a larger data set so that it's not just so easy that you would be able to come up with the answer by eye. That's really motivating. But the catch here is that the observations in the data set, the different variables, the different columns in the data set have to be things that very quickly your learners can understand. And really what can become kind of like an expert blind spot for us when we're teaching this is, especially if we come from like a particular domain. So for myself, from like the neuroscience or biology domain, I might, for example, think that using some deep sequencing data set might be a great example for this particular algorithm that I want to teach the students. However, that's because I have this deeper understanding of biological processes that you need to understand that data set. And depending on your learners, that data set might not be appropriate. So what you really want is, you don't want that so much of the students' cognitive resources spent time and energy trying to understand just what the data set is about, and then mapping that to the question, and then you see it just gets to be a bit too much. So instead, we want to use something where people understand what the observations are and what the columns are quite easily. So one example here from our introductory data science course is a data set from the Can-Lang-R package, where we have number of Canadians reporting a particular language as their mother tongue, so the language that they learned at birth. And then we have different categories. So in the data set, they use Aboriginal language as the category. It really probably should be Indigenous languages versus official languages versus non-official and non-Indigenous languages. Inspiration from this came again from Jenny Bryan. So she created the Gapminder R data package that's used quite widely in teaching R in many universities. And it's really nice because it's a biggish data set. So there's hundreds of observations in it. And the observations, though, are something most people understand. It's a country in a given year. And things that we're actually interested in, because everybody grew up in a country or more than one country in their lifetime, and we all grew up at a different time in history. And so those things make us generally maybe interested about asking questions with the data set. Also, the variables in the data set are country, continent, year, life expectancy, population, per capita GDP. These are all concepts that we, as adults, have an understanding of without having to have a deep explanation about it. So it makes it really accessible. So I've listed here some more explanations of data sets or data packages that might fit that. But the biggest thing is keeping in mind that it doesn't take a lot of time for your students to understand the data set, because that's, the data set isn't necessarily what you're trying to teach at that moment. My seventh simple rule is to provide a cultural and historical context for what you're teaching. And what this kind of is like, what do you mean by that? What I'm talking about is sometimes when we're teaching things in software or with software, things might seem weird or odd or strange. And it's really helpful to say why they are that way. If you give the history for why, and even tell students that this was a design choice. People thought about this and decided this was the best way to implement this, particularly, maybe for reason X, Y, and Z. It helps students understand, that tech software is built by humans, and so is going to be influenced by humans' perspective, human history, and human culture. And it helps prevent frustration or annoyances with the software. They can start to see the reason behind that. And why I think it's important to help prevent those frustration or annoyances, because I think for some people they can become real blockers. And make people maybe dislike or written up a certain piece of software, for example. So an example for this is when I'm teaching the programming language R with the tidyverse, where you see something that's quite different from a lot of other programming languages. So what is that? It's the heavy use of unquoted column names. So you think about anytime you're accessing a data frame column with the tidyverse, you don't put quotations around it. That's actually really strange when you come from other programming languages, and actually can make writing functions with the tidyverse a bit more difficult. And so some people coming, say, from Python or from Java or C coming into this situation might be like, that's a really dumb idea. But if they understand that R was written by statisticians for statisticians, and with the intent that much of the time would be typing things into the console or running code interactively, and not having to always keep track of opening and closing those quotes and making mistakes, trying to minimize that, then students can be like, I understand why that is a good design choice given that situation. Inspiration for this rule came from Colin Fay. He's a data scientist at Think R, and he wrote a really great post on why in R we use the arrow as an assignment operator. So he talks about that, and this can be from my experience, teaching students R can be very confusing. He talks about how R comes from another programming language named S, and then actually S was inspired by another programming language type called APL, and APL was designed for a particular keyboard that had one key that made the assignment operator. When you know that, then it makes a lot more sense as to why that design choice may have been made at the beginning. And maybe a bit more understanding and less frustration, and then maybe kind of digging into what does it mean now, and do we have to use it, and those sorts of things. if you're interested in learning more about the history of at least the R programming language, Roger Peng has a great section on it in his R programming data science book. Number 8 is build a safe, inclusive, and welcoming community. And I actually think, practicing this talk a couple times and giving it now, I might move this to number 1. This is probably the first thing you need to do when teaching in general at all, but I'm talking about data science, so I'm going to include it here. And what do I mean by this? It means that as the instructor, you should be putting in place scaffolding and guidelines to facilitate a safe learning environment. And that's your responsibility. And the reason for that is that students can't learn effectively if they don't feel safe. So if they don't feel safe to ask a question without being made look dumb, they're not going to ask that question. They're not going to be curious. If students don't feel safe to show up in the classroom because of maybe how they are talked to, just out, even just in the hallway or in on the course forum, for example, that's not setting up a good learning environment. So all of that kind of needs to be in place before you can have real expectations of student learning. It's a big responsibility, but it's one that we do bear as course instructors, I think. So one example of what it's not the only thing we do, but one thing that we do in our courses at UBC, or at least my courses at UBC, is that we have a code of conduct for each course. And that code of conduct holds a place of prevalence in the classroom. So we make time in the classroom to be like, here is our code of conduct. And we're going to highlight parts of it for you at the beginning of the course. It's very explicit. It talks about expected behaviors that will not be tolerated. It talks about what is the process for reporting something that violates the code of conduct, and who do you talk to? And if it's the instructor who violates the course of conduct, who do you talk to then? And all of this, I think, is really important for at least one piece of scaffolding to help students feel safe. Inspiration for me came from the carpentry's code of conduct. So for all of their workshops, they take this very seriously, and they apply that not just to their workshop setting, but even with all of the spaces that are considered under the carpentry. So, when instructors are getting together, working on material, at conferences, anywhere, their online discussion forums, everything is covered by this code of conduct. Number 9 for the simple rule is using checklists to focus and facilitate peer learning. So the pedagogical literature suggests that we can harness these communities of learning by having peers learn from each other, and peer review is one way that can happen. However, peer review can be really hard and difficult if you haven't done it before, or if it's reviewing something new that you're just learning. It's hard to know, what should I even be looking at? So what we can do as instructors, we're used to making rubrics for these things, so we can kind of hijack those rubrics and come up with review checklists. So here's an example of a data analysis checklist, a data analysis review checklist that we've generated for the Master of Data Science program courses. And what it does is it gives kind of the students a list of things to focus in on that we think are important for that assessment being completed to high quality. And then when we ask students to give comments and feedback, written feedback in addition to this checklist, they can focus their feedback in on the things they didn't check off, right? So if there was issues with tests, for example, and issues with the conclusions, they would not check those boxes, and then they would, in their review comments, really be able to know that that's probably what I should spend my time telling them about. Inspiration for this came from the R OpenSci organization. So this is an organization that reviews R packages, does peer review and publishing of R packages, and they use checklists for their reviewers. I've acted as a reviewer for this organization, and I can say that I personally found reviewing for that far easier than maybe I found reviewing for journals that didn't have these types of checklists. Because again, it's a great way for editors or publishing organizations to communicate to the reviewers what is important to them for their publication, what is really valuable, and it really helps focus your reviewer. This is becoming more and more prevalent in the publishing world. So the Journal of Open Source Software, the Journal of Open Source Education use this. There's now a PyOpenSci, Python package organization. And I think there's real value in these things in the classroom and outside. And finally, my last item on the checklist is to have students do projects. So what I mean is have students perform a data analysis project on a topic, ideally of their choosing if you can make it happen, from beginning to end. And this sometimes can feel daunting as an instructor, depending on how many teaching resources you have or how much time you have for grading. So that's why I put the word scoped here. You may have to say that the project has to be about this particular topic, has to use this particular data set, or it has to use this particular method, this particular programming language. So you can have some homogeneity for grading and making a rubric that's going to apply for everybody. But that can help make things scalable. And why do I think this is important? Well, I think it really helps provide students with motivation. We get lots of good feedback about courses that have projects because they have this flexibility and choice aspect that students really like. But it also gives students, good experience with messiness of real data. And we all know that in the real world, data is quite messy. So here's an example of a project from a collaborative software development course that I teach. And in this course, or in this project in particular, the students have decided to make an R package that extracts and analyzes song lyrics. And so they go all the way from taking the raw data and coming up with outputs from that raw data and all of the software and all of the version control and building of an R package that went into that. The inspiration from this comes from Stat 545, which is a course at UBC that Jenny Bryan created that was made before the Master of Data Science program. And in the classroom, Jenny would give lots of examples of teaching, the new concepts using that kind of like more tractable data set that's still rich and interesting, so the Gapminder data set. But then the students' homework was actually wrapped up into a project, which was working on something related to their thesis project. And so they got to be working in their discipline, but applying everything that they were learning in the classroom to that throughout the entire semester and wrapping up in a final project at the end of the year. So I'm going to now quickly run through these 10 simple rules that or remind you of these 10 simple rules that we just went through for teaching data science. So the first one, teach data science by doing data analysis and do that on day one. Use participatory live coding. So have the students watch you do things and have them do it with you. Give tons and tons of practice, and along with that, give tons and tons of feedback. Leverage, if you're using software in the classroom, leverage the automated software tests is one way to do this. Use tractable or toy data examples to build intuition, to build concepts. Once they have those concepts, add on real rich data sets that are more motivational and more real world, but keep them accessible. Provide cultural and historical context to the software and the tools that you're using to avoid frustration and blockers. Build a safe and inclusive welcoming community. Again, that should be number one. Use checklists to focus and facilitate peer learning. And have students do projects. Have them get an idea, get a sense of what the entire workflow is from beginning to end. And as I said, I'm standing on the shoulders of many other people giving this talk. I'm really just curating a list of good things I've seen in the data science education community that are already being practiced by so many other people. And here is a QR code that will take you to my talk slides, but I'll also paste those in the chat. And I'm happy to take any questions if there's time.
Awesome. Thank you so much, Tiffany. This is rules that I will hold it close to my heart when I teach my students. Wonderful. Thank you. And we have about a minute, and I think we can take one quick question. Is that right, Jessica? I know there's another networking session. We'll start 5:30 my time. Anyone? Maybe I can ask a quick one. I know that for intro courses, often students will be coming from various disciplines. Just in terms of the rules that you have shown us today, are there things you would emphasize, especially students from stats versus, for example, neuroscience? What are the components that you will emphasize more, and be sure that students are fully aware of and then do follow these rules?
Like if your classroom is more diverse, for example, is that your
Stats,
question?
yes, yeah. So students in stats, they may be interested in something totally different from students from neuroscience. So if you have
Yeah.
all that mixed together in one class, are there tips that you think you can maybe share with us quickly?
Yeah, I think using a variety of different types of data sets. So it's really easy, sometimes to fall back on data sets you're familiar with from your discipline or that you learned when you were going through education. But if you have a lot of different types of data sets when it comes to toy examples or those kind of more rich examples, but keeping them still accessible, that gives a little bit for everybody. So I think that is one thing that I would say. Yeah.
Okay, great. Yeah, very helpful tips. Thank you.
No problem.
Okay, so I think our time is up, and I wanted to be sure we follow the rules of
No problem.
on time. Okay, that's all. Thank you so much, Tiffany. And all right, so it's time. I guess I'll hand over to Jessica and Jane.